In section 10.2, we're going to talk about inferences for two population means using independent samples. And our assumption here is also that the population standard deviations, although unknown, but they're going to be assumed to be equal. In section 10.5, which we'll go after this, in section 10.5, we'll actually look at the case where the assumption of independent samples are going to be removed, and we'll see how we can address that in section 10.5. But in this section, the assumption is that the two samples are independent. Okay, so coming out of section 10.1, we talked about inferences for the sampling distribution of two population means. And from the takeaway from section 10.1 was that in order to compare two population means, that's mu1, mu2, two population averages, we're going to use the difference between the means, the two means, to compare them. And depending on the difference, whether it's positive, negative, or zero, then we can make statements as far as which average is higher, lower, or are they the same. So we mentioned in section 10.1 that a single guess, one number, point estimate of the difference in the population mean is going to be the difference between the two sample means. And we also looked at the sampling distribution or probability distribution of this random variable x bar 1 minus x bar 2. So once we know the probability distribution of x bar 1 minus x bar 2, then we were able to actually make a probability statement in section 10.1 about x bar 1 minus x bar 2, and we answered the probability statements. In this section, we actually want to construct confidence interval and do hypothesis test for mu1 minus mu2. That is the difference in the means of the population. So from section 10.1, we have the sampling distribution of our statistic x bar 1 minus x bar 2 is either going to be normal or approximately normal, depending on whether we sample from a normal population or not. The center of the sampling distribution turns out to be of this statistic turns out to be mu x bar 1 minus x bar 2, and this is the deviation of that normal distribution, this normal distribution. And then we also mentioned in section 10.1 that mu of x bar 1 minus x bar 2 will be mu1 minus mu2, and sigma of x bar 1 minus x bar 2 is going to be square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Now, the question before we actually look at the formulas for confidence interval and hypothesis test, here I have a question, pose the question here for us. So remember, the assumption is that these two deviations are unknown but assumed equal. So what do we use in place of sigma 1 and sigma 2 if they are unknown? Remember, this is unknown but assumed equal. So to answer this, I'm actually going to show you this one example. Let's say I have two hypothetical populations. So these are the scores on some variable in the first population, and these are the scores on that same variable in the second population. Now remember, the assumption is that the deviation of these two are going to be equal and unknown. So suppose I take a sample of size 10 from this population and a sample of size 50, 5 times that number from the second population. Let's say the standard deviation in the first population that we sampled from for the sample turns out to be 15, and the standard deviation of the second sample of size 50 turns out to be 20. Now remember, in the population they're supposed to be the same. However, we know that if we sample, most likely our sample numbers are not going to be exactly the same. So do I use 15 or do I use 20 if the assumption of equality of deviation is made? And here I have, are these the same? And clearly the sample deviations are not, but in the population they're supposed to be. So which one should we use? Should I use S1 from the first sample, or should I use S2? Now, the sensible answer would be this. Why don't we average them? I cannot say it's 15, and I cannot say that it's 20. Because if I say it's 20, I've ignored information in this one. And if I say it's 15, I'm ignoring information in the second sample. So why don't we average them? I guess that would be sensible. Now, averaging them assumes that the samples are the same size. That's when we average. If the sample sizes are the same, that would make sense. But it's not really fair to this number, the 20, because it's based on a sample of size 50, which is 5 times the size of this sample, first sample. So it looks like, to me anyway, it looks like we should give more weight to 20 than we do to 15. So why don't we weight the averages? So how are we going to weight the averages? In other words, we use a weighted average. Here's a formula that we're going to do. We're going to actually, what they call pooling them. We're going to pool these deviations together. So the formula now is this: S squared pooled, and for short I've written that as S squared sub P. And here's a formula that we have. The way it's averaged based on the sample size. We do N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared over N1 plus N2 minus 2. So this is the way they pool them. Now, to give you an example. For the example I had above, remember S1 was 15, S2 was 20. So I've done the formula there. Sample size 10 minus 1 times 15 squared plus 50 minus 1 times 20 squared divided by 10 plus 50, that's N1 plus N2 minus 2. You work the arithmetic using a calculator. I got this number, 372.84. Now this S squared P is the pooled or average, weighted average, and it is the variance, not the deviation, because it's in squared units. So to find the standard deviation, pooled deviation that is, we'll take the square root of the number above, and that number turns out to be 19.31. Now note here, by the way, that this number 1931 lies between 15 and 20, so it is kind of average between them, but not exactly halfway. And it's closer. 19.3 is much closer to 20 than it is to 15, right? So it is doing what it's supposed to be doing, the formula for us. And this is the formula that we're going to use in constructing confidence intervals and test our hypothesis test. Now, just want to point something here out. If the sample sizes are the same, or pooled variance actually turns out to be the same as if we just straight average them. And I'm showing that for our example that we just did. I just changed the sample sizes to 60 each. So N1 is 60 and N2 is 60. So I went through the formula once again, and once you get to this point, I actually factored, that's 59, that's 59, so I factored the 59. And in the denominator, of course, you have 120 minus 2 is 118, and you can divide out the 59s, and there you go. It looks like I averaged the two variances, right? The first variance plus the second variance divided by 2. And that's what I was saying, that if the sample size are the same, you could just average the two variances. And that's just our ordinary average of two numbers. So anyway, I just want to point that out. And of course, this pool deviation ends up to be 17.68. Okay, so just want to, again, make a note of that. Now, so let's actually see the formula that we want to work with. This is the formula that we're going to use in order to construct the confidence interval for mu1 minus mu2. So it's going to take the point estimate, x bar 1 minus x bar 2. Those are the sample means. We're going to subtract the second sample mean from the first one, plus or minus. Then we have a t multiplier. We saw this t also in chapter 8. Times square root of s squared sub p, that's our pooled variance, times 1 over n1 plus 1 over n2. We'll see the formula that's in the book in a minute. It's a slightly different than the one I have, but they're both the same. And of course, our t will have a degrees of freedom. The degree of freedom is n1, n sub 1 plus n sub 2 minus 2. So that's going to be our degrees of freedom. And the quantity that I have underlined to the right of plus minus, just like in chapter 8, this expression is the margin of error for our confidence interval. Okay, and I'm echoing the formula for pooled variance here once again, because this formula is used here. Okay, and when we do hypothesis test, for our hypothesis test, the null hypothesis says the two means are the same. Against the alternative, remember, could be any one of the three forms that is not equal to, it could be less than, or it could be greater than. Our test statistic we're going to use for test of hypothesis in this section is t, and this is the null symbol. That means t under the assumption of null. T sub 0, think of it, is equal to the numerator x bar 1 minus x bar 2 over the denominator. Now, one thing I want to mention about this denominator, what you see in here, actually, right in here, this thing is exactly the same as what's right up here. You see that? So there are similarities in the formulas. So once you calculate that square root, you can use it in the confidence interval, and you can also use it in the hypothesis test. Just want to point that out. Okay, and of course our decision rule for the hypothesis test, once we have that, is we're going to reject if the test statistic, that's t sub 0, falls in a rejection region, and that's using the critical value approach. And if we use the p-value approach, we're going to reject the null if p-value is less than or equal to alpha. That's the p-value approach. Now, for our t-tests, we get the p-values from StatCrunch. Remember, we cannot get those exact numbers from the table. So the best we can do is, like, say, is less than, greater than, or between two numbers. That's if we use the table, but we're not going to do that. We're just going to use the StatCrunch in a few minutes. And there you go. So here are the formulas that are in this section. First of all, what we're doing, it's commonly called a pooled t-test. And what is it for? It's because we would like to compare two population means. Now, the assumptions are important, by the way, folks, because if you don't go with these assumptions, sometimes the procedures are not valid. Our first assumption that we've had throughout since chapter 8, this assumption is not going to go away for us, by the way. In every chapter, we always assume we have a simple random sample with replacement from a finite population, or we have a simple random sample without replacement from a very large, very, very large population. Okay, and our second assumption here is that the samples are, let me enlarge this so you can see better. So the samples are independent. The third assumption is normality of the variable, in normality of random variable x over both populations. Or large samples. N1 is 30 and so is N2, at least 30 each. Not combined, but each of them must be at least 30. And finally, the fourth assumption is the assumption of the section, that we have equal population deviation, but they're going to be unknown but equal. So our alternative hypothesis could be two-tailed, could be left-tailed, and it could be right-tailed. And once we're given the significance level, the problem will give us alpha. And here's our test statistic. That's t sub 0 that we saw earlier. Okay, so maybe the author should have put that. There you go. That's what this is. That's t sub 0. That's the test statistic, assuming the null is true. Okay, and of course the formula for pooled deviation is what you see here. Now here's, by the way, what's different from what I have versus what's in the book. See that SP on the outside? The formula I have up here, I moved SP on the inside the radicand inside. So SP on the outside becomes S squared P on the inside. And that is exactly right in here. You see that? Mine is on the inside. The author's places that SP on the outside of the radical. And once we have that, then our test is pretty much the same again as in chapter 8 and in chapter 9. For chapter 9, hypothesis test is what we're doing now, so it's chapter 9. And there you go. This is our t-test. Using critical value, we reject if we fall into a rejection region. And remember, these rejection regions are determined based on the alternative. That means two-tailed. And also based on alpha, the stated probability of a type 1 error. For the left tail test, we reject in the left tail. A right tail test, we reject in the right tail. Using p-value approach, simple and clean, you reject if p is less than or equal to alpha. That's when we reject the null. Okay. Now here the author has a note. I'd like to have your attention on this. This procedure that we do, the t-test, is fairly robust, by the way. It's a robust test. But the test of hypothesis will be exact if population we sample from are normal, and they're approximately correct if the sample sizes are large from any population. Remember, large for us, according to central limit theorem, means 30 or more. So each of the samples must be at least 30 if the assumption of normality is not made. The formula for confidence interval, I had that, and here it is. This is what the author has. So we're going to be doing a pooled T confidence interval procedure. Same four assumptions, by the way, that we have for hypothesis tests. All the assumptions for hypothesis test and confidence intervals will be identical. So we have exact same assumptions here. The degrees of freedom in both hypothesis test and in confidence interval for our T is going to be n1 plus n2 minus 2. And here's the formula I had. Again, what's different from this formula than the one I had above is I moved SP inside the radical and wrote it as S squared P. This way I don't have to take square root of S squared subscript P, the pooled variance. I can use just the variance without taking the square root of that, because that's just gonna, the minimum it'll do will produce more rounding error. And there we have it. So let's take a look at an example. Now, what we're doing in this section, by the way, and in all of chapter 10, we will be able to do in StatCrunch. And I'll show you how that is done in a few minutes. So in this exercise number 36, the question reads, we have provided summary statistics for independent simple random samples from two populations. In each case, use the pooled t-test and the pooled t-interval to conduct the required hypothesis test and obtain the specified confidence interval. So first, we're going to do the hypothesis test. Now, whether you do confidence interval or hypothesis doesn't matter. We have to go through computation of pooled variance. So I just used the numbers that we were given, and here's how I calculated our pooled variance. Our first sample size is 10, so that number goes here. S1, that's the first sample deviation, 4 goes here. You square it because S1 needs to be squared. These are variances. What we're given are deviations. And the second sample size 15 minus 1, S2, that's the second sample standard deviation, 5 squared divided by combined sample size minus 2. And you carry out the arithmetic, and on a calculator you get 21.48 is what I got. That's an estimate of the common variance that we assume they're equal. That's a point estimate of that common variance. Now, in order to conduct the hypothesis test, we are given that it's left-tailed and we're given alpha. I need those two things. We don't need any data. We just need this statement, the type of hypothesis, and our significance level. And what we can do is we can actually find the critical values. And there you go. This is a left-tail test. So the rejection region, that means rejection region is on the left tail end of the distribution. This is a T-curve with 23 degrees of freedom. The degrees of freedom for this T is exactly the same as the denominator of our pooled variance. The number I got is negative 1.714. And how did I get that? I got that from the T table in the back of the book. And there it is. Remember, 23 degrees of freedom. Now, the T in the back of the book actually gives you the area to the right, correct? So this is the area that it gives me, area to the right. And what we want is actually the area on the left side here of the distribution. So I can use the symmetry, right? Whatever is to the right, you reflect it about the center and you get the tail area on the left side. So 0.5, significance level, and less than. So the 0.5 and 23 degrees of freedom. So I went to column 0.5. Let me enlarge this again so you can see better. So I went to the 0.5 column and scroll down to 23 degrees of freedom. The row and column where the two meet, 1.714. That's the area to the right, 5%. By symmetry, the area on the left, 5% will be exactly the same. And there you go. We have that negative 1.714. So once we calculate our test statistic, if it's exactly equal to or below that, if it's less than that, we're going to reject the null. That means it's too far away from the center. So our next step, I calculate our test statistic. Test statistic turns out to be negative 1.59. And you can kind of go through this on your own and see what I've done. I simply plugged in for all of these quantities that were known. S squared P was 2148 from a step above. And then work out the details, and I got negative 1.59. Now this number in the denominator, remember, the denominator of your test statistic, you also use that in the confidence interval. So I just want to point that out, and I've written here. This number will be used for confidence interval also, so we don't have to redo this twice. So our test statistic is negative 1.59, and here's our drawing. Negative 1.59 does not fall into a rejection region. So as a result, we're not going to reject the null hypothesis, right? And here's our rejection region again in the tail. So we're not going to reject this null. And that would be the conclusion of this exercise. We're going to fail to reject the null hypothesis. Okay. Now, let's take a look at our confidence interval. They ask for 90% confidence interval. That makes alpha 10%, half of that 5%. The T with 23 degrees of freedom and 0.5 now. Remember, we already found that number from previous step. From part A, that's 1.714. Now remember, this is a positive t-score for confidence interval because it's subscript T sub 0.5 means area to the right. So I'm using the positive 1.714. And then here's the formula. I plug into the formula and this is what I get. And work the arithmetic of what we're doing here, negative 3. Once you add 3.243, another you subtract, and this is what I got. So our confidence interval runs from negative 6.2 to upper limit of 0.243. And when you write your confidence intervals, by the way, just to point out, we always put the smaller number on the left and the larger number on the right side, to the right. Okay? And that completes that exercise. Now, let's actually take a look at a word problem. And we're going to do everything we've done in this word problem. Okay? And we'll be able to go to StatCrunch for this one. So in this exercise, doing time, the problem reads, the Federal Bureau of Prisons publishes data in prison statistics on the times served by prisoners released from federal institutions for the first time. Independent random samples of released prisoners in the fraud on firearms offense categories yielded the following information on time served in months. So you can kind of see the data here. These are the people that committed fraud, and these are the ones that committed firearms. And judging from the numbers, by the way, it seems as if the numbers for firearms, these are bigger overall. They're bigger than these. Of course, in the case of fraud, you do have a number. The highest is 16.6, right? Which is bigger than some of the time that was served for firearms, like in this case, this one and this one and this one. But majority of time served with firearms exceeds that of fraud. Now, at the 5% significance level, that's our alpha. Do the data provide sufficient evidence to conclude that the mean time served for fraud is less than that for firearms offenses? So we want to test the hypothesis. And they give us the summary statistics here, by the way. See these? We know that by summary statistics, remember, we mean the sample size, the sample mean, and the sample standard deviation. And we're given all of those. We're given the sample mean, sample deviation for fraud group. We're given the sample mean, sample deviation for the firearms. And remember, each of these samples are size 10. That's 10 here and 10 here. So, the fact that the question reads, can we conclude the mean time served for fraud is less than that for firearms? Okay, so here we have less than. That means the alternative has to be less than, correct? Because the alternative cannot have equal sign. And we always take the null to be equal, right? Keep that in mind, please. The null here always reads mu1 equals mu2 in this chapter. The alternative is left-tailed. And what are mu1, mu2 here? Well, mu1 is the average time that's served for fraud. Mu2 is the average time served for firearms. And before we actually look at our test statistics, our formula, we can actually determine our rejection region. So in order to determine critical value, we need to know the significance level alpha and the fact that the alternative is less than. These are the two pieces of information we need. And here is what I got from that table again. You can go to that table and see that if you look at the T with 18 degrees of freedom and the area 05, now remember the T table gives you area to the right. We're going to reflect it by symmetry, get the area on the left. So I'm going to go above here in a moment and confirm this number. 18 degrees of freedom and 05, right? And let me see if I have it here. No. Okay, let me go back. 18 and 05. And here it is. So we are in the 05 column, and this time 18 degrees of freedom right here. And again, that would be 1.734. That's this number, 1.734. So that's how I got 1.734 for this exercise right there. Okay. Now, so once we calculate our test statistic, if it falls into this region, we're going to reject it. Otherwise, we do not reject the null. So I calculate the pooled variance like we did twice before. The pooled variance is about 22.77. Now, square root of that, by the way, will be a point estimate of that unknown but equal deviation that we started the section on. Our test statistics is going to be the formula we had above. So I worked out this test statistic and I got negative 4.06. The denominator actually 2.134. We're going to use that later for confidence interval. Okay. Now, because the sample size, by the way, is equal, we could have averaged the two variances and found our pooled variance. That is up here, that is. But it's okay. Just go through the motions with the formula because not all the time they're going to be equal. So, once we have our test statistic, we go and compare that to our rejection region. It looks like this value of our test statistic actually falls into a rejection region, deep into that rejection region. So we're going to reject the null hypothesis. The null said they're equal, the alternative said no. You do less time for fraud than you do for firearms. Now, this is almost, by the way, this negative 4, if this was a standard normal distribution like Z, this would be about 4 deviations below, right? So it's like, how many deviation below is it for the T? I just have a note here for you, for those that are interested. The standard deviation of a T distribution is given by this formula. It's the square root of degrees of freedom over degrees of freedom minus 2. So for this exercise, degrees of freedom was 18, divided by 18 minus 2, square root of that is 1.06. As the degrees of freedom increases, by the way, this ratio approaches 1. And you can see here, it's going to be 1, which means almost the standard normal distribution. Because the T has center 0, its deviation isn't quite 1. But notice again, it's almost 1 standard deviation. So this T, calculated T value of negative 4 means I'm almost 4 deviations below, which is too far into the rejection region. Not quite 4, it's something like 3.8-ish, something like that. But anyhow, so what is our decision and what is our conclusion? The decision is pretty generic. Your decisions are always, do you reject or do you not reject? That's your decision. It's the conclusion that we always interpret our decision in context of the word problem or the research we're doing. So the conclusion here is that the average time served for fraud is less than that for firearms. That's our conclusion. And we're done with that exercise. Now, using p-value approach, since alternative is less than, then our p-value is written this way, the way I have it. P-value is probability of t less than our test statistic. So it gives you the likelihood of the sample results like we got. That's our p-value. And it turns out to be 0.0004. That's pretty small p-value, which means we have clear and convincing evidence against the null. Okay, it's far beyond reasonable doubt for this exercise. Okay, now using StatCrunch, by the way, I found it, and just to show you, this is how I found it. And we can go to StatCrunch and I'll show you how I got it, but there's no need for that because the output we actually get will have the p-value on it, so you don't need to do it separately. Okay, so here's our p-value, but so I went to the probability calculator in StatCrunch, 18 degrees of freedom, and the t-score was negative 4.06. Probability of less than that is going to be 0.003674, which rounds to 0.004. Okay, now since our p-value is much less than 0.05, we're going to reject the null. Of course, you get the same conclusion, right? So in this case, the evidence is extremely strong against the null. Now, one thing I want to point out here, as I have written, we just rejected this null hypothesis, true? Now, remember when we talked about type 1 error, that's back in chapter 9. Type 1 error was rejecting the null when in fact it is true. Because everything we do is based on sample, so nothing is definitive. So that's why the result of one research may change in a later time, because the sample will represent a different representation of the population. So the question might be, well, what is the actual probability of a type 1 error now? What is the probability that we rejected it and we made a mistake? That's what p-value tells us. The actual observed probability of a type 1 error is 0.004. That means there is a 4 in 10,000 chance that we committed a type 1 error when we say reject the null. Okay, but then the other side of that is 10,000 minus 4, that's 9,996. 9,996 out of 10,000 times we are making the right decision. So that's the risk we're definitely willing to assume. That's pretty small p-value, so the evidence again is extremely strong against this null. Now, because p-value is the actual observed value of probability of a type 1 error based on observed value, it's called an observed significance level. Remember, we talked about significance level as alpha, the size of our test, but the p-value is actually called the observed significance level, and OSL for short. So now here's the run of a StatCrunch, and we'll go over this in a few minutes and I'll show you how I got these numbers. Okay, but in StatCrunch, that's how we actually got these numbers. And I'm going to get these numbers in a few minutes for you. I'll show you how this is done in StatCrunch. So this was again exercise in chapter 10, section 2. So if I go to the page of the book, I want to make sure I have this exercise, and then we go to StatCrunch. I'll show you how this is done. Okay, now, and you can see, by the way, here, you can see this is our test statistic. It's pretty close to what we got. The standard error here is 2.134, right? Our standard error, 2.134. And if you go up here, where is it? There you go. This is 2.134. You see that? That's what that number. So StatCrunch will give you this number also, 2.134. And let's see, this should come up. There you go. And the rest of it is our p-value. P-value is 0.004. Okay, so how did I get this output, correct? Let's go to StatCrunch and do this. So the way we go to StatCrunch is, again, through MyMathLab. That's how I go through this. And so I'm going to go to StatCrunch. And I'm going to data set from your textbook. That's the one I'm going to use. Now in here, let's see. Chapter 10 are the exercises. Now exercise number 39 is this one. There you go. So in this exercise, here's the data that you see, but remember they gave us the summary statistics, so we're going to run it both ways, using summary statistics and using the data itself. So here's how we do this. You go to stat, and then we go down to t-stats. And this time we have two samples. Remember, one sample, this is for chapter 9. So we have two samples now. On our two sample, I'm going to put with summary. So our sample 1, remember this is the sample for fraud group. The sample mean for fraud, that was x bar 1. That was 10. So let me hook up my keyboard here. Okay, so our sample mean is 10. That's 10. The sample standard deviation was 4.9. And the sample size in both cases are 2, 4, 6, 8, 10. 10 each. 10 here. And for the second sample is also 10. The second sample mean, this is for the firearms group. The mean was 18.78, almost 19 months. And the standard deviation is 4.64. And note, by the way, the standard deviations, how close they are. This is 4.6, 4.9, not too far. So that assumption that the two deviations are equal is not far-fetched assumption. And now in here, this is important, folks. You see right in here, calculation options. The default was recently signed or changed to off. So that means we need to turn that back on. We're pooling the variances here. Now this pooling is important for us, by the way, because in chapter 16, which we do right after chapter 10, we're going to be doing the same thing in chapter 16. So, and then you go down here, perform. We're doing a hypothesis test. The mean is equal. The alternative was you do less time for fraud, right? So it's going to be less than. And that's it. So this information is put in and compute. And there you go. So you're gonna, let's see, what did I do wrong? I did something wrong here. Sorry, folks. Let me go options, edit, sample mean. I didn't put the right sample mean. It was 10.12. 10.12. Sorry about that. 10.12, 4.9, and then 1878, 4.64. Those are right. Now let's. Everything else is good. Compute, and now that's better. This is what I had in my notebook. So our test statistic is this. Right in here is our test statistic, and this is our p-value. Just want to show you how I got it. So this is using summary statistics, right? Now let's run this again. This time I'm going to use the actual data. So here's our t-test, again t-statistic for 2 samples with data. And this time our results going to be off by a little bit because the StatCrunch doesn't round like your textbook does. So the variable for the sample, first sample is in the fraud, and the second sample is in firearms. We're going to pool the variances together, and the alternative was less than, just like before. Notice there's no need for me to put the sample size, the mean, or the deviation. StatCrunch can figure it out based on the actual data. And there you go. Our p-value is exactly the same. Our test statistic is about the same. So not much of a difference there. Okay. So this is how you do this in StatCrunch. Let me go back to my notebook, and that's how I got this output. Now, a continuation of this work. Let's say we want to do a confidence interval for the same exercise. This time we're doing a 90% confidence interval. So here's our formula. And remember that number 2.134, we got this from our test statistic. This was the denominator of our test statistic. And this is a left tail test. Our critical values, remember those that we found, happen to be the same here. Because I need this t multiplier, right? T alpha over 2. So I'm showing you how you get that t score. For a 90% confidence interval, alpha is 10%, half of that 5%. Degrees of freedom 18. So you're looking at 0.5 and 18 degrees of freedom. I went to the table, the t table, and that's the number you get. So you have plus minus. There's plus, there's minus, your t score. And pretty much everything we have it from before, right? This is the x bar 1 minus x bar 2. That was the numerator of your hypothesis test. And the square root was the denominator. And this t score even, the way author made up the confidence interval is that we don't need a different t score. So there you go. I have put that together, and our confidence interval turns out to be from negative 12.38 to negative 4.98 months. Okay, now this is, remember, what's to the right of plus minus is our margin of error. Now we'll revisit this in the end. I'm gonna try to interpret that for you. That's what I mean. We'll revisit this in the end. It is the margin of error. And now here's how we're going to interpret this negative confidence interval. Okay, like what is negative 12 to negative 5 months almost? What does that tell me? So what I've done is actually this. At the lower limit of negative 12.38 months, remember that's an estimate of mu1 minus mu2. If mu1 minus mu2 is at the low end, negative 12.38, then here I move mu2 to the other side, and mu1 is mu2 minus 12.38. Now, what does this equation tell me? Remember, mu1 was the average time served for fraud, and mu2 was average time served for firearms. So, the difference of negative 12.38 here on the right side, it tells me that the average times served for fraud is 12.38, a little over 12 months, a little over 1 year, less than that for firearms. So that's what that tells me. At the high end, the larger number is 5 months. So when you put 5 months, then you get the average time served for fraud could be anywhere between 12 to 5 months less. You do less time for fraud, or you would expect to do less time for fraud than you would for firearms. Now I'm trying to interpret that another way. If this time, take mu2 to the other side, and bring 1238 to the other side, becomes positive. Negative moves becomes positive, the other side. And this time it's saying that mu2, the right side, mu2 is mu1 plus 12.38. Another way to say the same thing we just said up here is that the average time served for this time firearms, mu2 is firearms is 12 months more than average time for fraud. So it's another version of what we just said up here. So these two statements, what's up here, this one, and this statement, they're the same. They really tell us the same information. And I did that just so I can write this statement. So what does the negative, again, confidence interval mean in this case? It means on average, you could do anywhere from about 5 months to 12.38 months more time for firearms than for fraud. And we make that statement with 90% confidence. And this is now the run from StatCrunch. And I'll show you how to do that in a moment. But you see these numbers we got. That's negative 12.3. Well, we have 3.8, 3.6, close enough. And on the high side, we had almost 5. They got almost 5. So this U here means upper. So you're looking at the upper limit. And the L here means lower limit. Upper limit, lower limit. And on average, you do 8 months, almost 9 months, rounded to the nearest month. Almost 9 months less for fraud than you do for firearms. Now, to show you how I did this in StatCrunch, I'm sure you want to wonder. So remember, we just did this hypothesis test, right? So if you edit that, and instead of hypothesis, click on confidence interval, and put your confidence level. It was 90 for us. And this is how I got that confidence interval from StatCrunch. Okay, so once again, how you do this, you go to Stat, T-Tests, T-Statistics, to sample, either with data or with summary. Let's say with summary, and then there you go. That's how you do your hypothesis test confidence intervals. Okay. And Now the one thing, so we're done with this exercise truly, but lastly, how do you interpret the margin of error for this problem? Remember, the margin of error is what's to the right of the plus minus in the formula for confidence interval, which turned out to be about 3.7, right? So here's how you actually interpret this number. When we estimate, or when we say that on average you spend about 9 months less for fraud than you do for firearms, that estimate of 9 months could be off by no more than 3.7 months. And we are 90% confident about that statement. So that's what the margin of error is. It's the maximum error of estimation. That's no more than that. Could be less, but no more than that. Okay, so just want to put that out there. So the moral of this story, and we're done with this. So I have this little thing in the for you. So if you should commit a crime, you have an option or a choice between fraud or firearms. The recommendation based on this data is to commit a fraud. You expect to do less time rather than firearms. And it could be more lucrative. Who knows? Okay, so we're done. And with this, we conclude section 10.2. We're going to omit section 10.3 and 10.4. After this, our next lecture is going to address section 10.5, where we change the assumption of independent samples to paired or dependent samples. So until then, we're just going to sign off for now.